One of the applications for integration is kinematics. We learned when we did differentiation that there is a relationship between the functions of position, speed, and acceleration through the derivative. We learned that the derivative of the position is the speed, the derivative of the speed is the acceleration. For integration, the role is going to be quite the opposite. The integration of the acceleration with respect to time is going to be the speed, and the integration of speed is going to give you the position. In this last integral, we need to have a little bit of more care because we have one of three options. The first one is we can create the function that represents the position of an object at any time t, s of t, by taking the indefinite integral of the velocity function and integrating it with respect to t. This, with some initial conditions, should help us identify what is the function or that represents the path of the object. The second option is consider a definite integral. In this case, we're going to have 2 points in time, one a and the second one b. A is going to be the starting point of the movement and B is going to be the ending point of the movement. Now the particle is going to go from A to B following a specific path. A definite integral can help us calculate both the total distance traveled and the displacement, so we need to be very careful on how we do that. The displacement is the distance following a straight line from the starting point of the movement until the end point of the movement. The displacement d is calculated as the integral from A to B of the velocity with respect to time. However, we have the total distance traveled is going to be the total length of the path of the trajectory that the particle or object followed whilst going from the point A all the way to the point B. So in the case of this diagram, the total distance traveled will represent the length of the pink curve. This distance is going to be calculated as the integral from A to B of the absolute value of the velocity with respect to time. Now the displacement is going to be measuring the distance between the starting and end points following a straight line. So it could happen that if our starting point and end point is the same, the displacement is going to be equal to 0. However, you can have a displacement equal to 0 with a total distance traveled that is not 0 if the particle is following a circular path or a closed loop. Let's take a look at some examples on how we're going to apply this knowledge. For our first example, we have a function that is v of t given by sine of pi t is the velocity in meters per second of a particle moving along the x-axis. We have three small tasks. The first one is determine when the particle is moving to the right or to the left and stopped, and if it stops, determine if it changes direction at that time. And then B, find the particle's displacement over this interval, and then find the particle's total distance traveled for the interval 0 to 3. So let's begin with A. We want to know when the particle is moving to the right and moving to the left. The way that we are going to know that is by considering changes in sign for the velocity function. A function will be moving to the right if the velocity is positive and will be moving to the left if the velocity is negative. It will have stopped if the velocity is 0. So let's begin with finding all the values of t for which sine of pi t is going to be equal to 0. And we know that this is going to happen every time t is an integer multiple of pi. So this is going to be 0 whenever t takes the value of 0, 1, 2, 3, etc. Now we know that before changing direction, that particle has to stop. So at which of these times that we found is the particle changing direction? Sine is a graph that starts at 0, 0 when the time is 0 and will go up towards the maximum first. Therefore, it's going to go half the period positive, the second half of the period will be negative. So there is a change in direction within the first half of the period. Now this function is going to have a full period at time equals 2. So from 0 to 1, the function will be positive, meaning the particle will be moving to the right. And from 1 to 2, the function will be negative, meaning the particle will be moving to the left. Now at 2, there is another change of direction as the cycle repeats itself. So from 2 to 3, the particle will be moving again towards the right because the sine function will be positive then. Now B, find the particle's displacement for the time interval from 0 to 3. So B is going to be done through the integral from 0 to 3 of the function sine of pi t with respect to time. So if we do this integral, we're going to get minus cosine of pi t divided by pi, and evaluated between 0 and 3, this is going to be equal to minus 1 over pi cosine of 3 pi minus cosine of 0. So that is equal to minus 1 over pi. Cosine of 3 pi is equal to minus 1. And minus cosine of 0 is 1. So the final answer is 2 over pi. Now for C, we have to do the total distance traveled. So in this case, the integral that we have to calculate is the absolute value of sine of pi t dt, which if we do in the calculator, we can just go right away and input this. And if we're doing it by hand, means we have to split the integral. We need to do the integral from 0 to 1. As the particle moves to the right, it's going to be positive, so sine of pi t dt. And then we're going to take away the integral from 1 to 2 of sine of pi t dt, and then add the last part of the integral from 2 to 3 of sine of pi t dt. And once we calculate all of these integrals, we get that the total distance traveled is going to be 1.90985, etc. So to 3 significant figures, this is going to be 1.91 meters to 3 significant figures.